Hello everyone, in this video we're going to talk about graph coloring. So what is graph coloring? So graph coloring is used when we need to assign resources so that objects that conflict with each other receive different labels or colors. So more specifically in this video, we're going to talk about vertex coloring. That means in the graph you have vertices and you have edges, and we're going to color the vertices so that we can assign resources to the vertices that conflict with each other so that they have a different color or different labels. Okay. So for vertex coloring, it's an assignment of colors to the vertices of a graph. There's enough definitions I want to give you here. That is, the vertex coloring is called proper if any pair of adjacent vertices have different colors. So vertex coloring is called proper. And I want to highlight the word proper here. So if any pair of adjacent vertices have different color. So for instance, if we have this type of graph, you have one vertex, you have another vertices, and these two vertices are connected together by an edge. And these two vertices, let's say this is V1, this is V2, and V1 and V2s are adjacent to one another. And as you can see in this picture, I illustrate that the vertex V1 has one color and the vertex V2 has a different color. So in this case, you have V1 to be a brown color and V2 is purple. And this graph right here is a proper vertex coloring. So this graph represents a proper vertex coloring. Another example I want to include here is that I have a third vertex here and I have V, and I have this to be V3. And because V1 and V3 are not adjacent to one another, because there's no edge connecting these two vertices, then the vertices that are not adjacent to one another can use the same colors, right? And I can certainly do the same thing here when I compare the vertices V2 and V3. I can certainly color V3 to be a purple because V3 is not connecting to V2, or V2 and V3 are not adjacent to one another, so they can use the same colors. And the number of colors that we use in the graph coloring is called the chromatic number. And is denoted as x of g, or chi in the Greek letter. So the chromatic number is the smallest number of colors necessary to get a proper vertex coloring. So it is the smallest number of colors necessary to get a proper vertex coloring. So in this example that we are working right now, the chromatic number is 2 because you use two different colors to color the vertices. And the use of graph coloring is turned out to be very useful in a lot of real-world applications. I'm going to bring up two applications here in this video, but certainly you can find more when you go through the textbooks. Alright, so the first example I want to bring up is called the signal interference of wireless network. So signal interference of wireless network. So the wireless network in our society should include cell towers, right, to send out the signals. And we're going to use vertices to represent the cell towers. Right, so the vertices that you have in graph theory can be used to indicate cell towers. And the edges in graph theories are used to indicate that the towers are close enough to create interference with one another. So towers that are close enough to create interference with one another. And we're going to do the last part here in order to avoid this signal interference. What you do is that you assign different colors to any cell towers or any vertices that are adjacent to one another. So when you provide different colors to adjacent vertices, what it means is that you're going to assign a different frequency channels for that cell towers. Assign different frequency channels to cell towers. Okay, so that's one application, and it makes sense, right? Because you don't want the two cell towers right next to one another and with the same frequency, and they go into interface with one another. Not only for the wireless network that we have, it's not only for cell phone but also for radio signals as well. Another applications of graph coloring is pop up a lot in education, especially in course scheduling. So this is the example of course scheduling. So you're working on the projects to assign courses for the university, right? And you want to make sure that any two lectures with a common student occur at different times to avoid conflicts, right? And of course, this is a very small problems to have for our example, but when you actually working on the project for the university, the problem become exponentially more difficult. But the premise for this example is still on the same idea of course scheduling. Right. So again, you want to make sure that any two lectures with a common student occur at different times to avoid conflict. And of course, we cannot schedule two courses at the same time if there is a conflict. Right? We don't want to do that at all. But at the same time, we would like to use as few separate times as possible. We cannot just take up 24 hours of a day and to assign every single course in the university. That's too much and nobody going to take it. So there's certain constraint that you need to follow, of course. So the first one is that you cannot schedule two courses at the same time if there is conflict, and you want to use as few separate times as possible. That's going to motivate the use of a vertex coloring, and we're going to dive a little bit deeper into this particular example. So let me write down to the setup first, and then I'm going to break up some images for us to do the vertex coloring. So what you do here is that you want to make sure that any two lectures with a common student occur at different times to avoid a conflict. So the constraint is that you cannot schedule two courses at the same time if there is a conflict. So cannot schedule two courses at the same time if there is a conflict. And the second constraint that we want to follow is that we want to use as few separate times as possible. So how the schedule going to look like? So again, this is just hypothetical scenario. I'm going to bring up some courses related to mathematics and computer science and see how would you use graph theory to avoid conflict in course scheduling. So in this example, you have a few different courses here. So Calculus 1, Discrete Mathematics, Linear Algebra, Data Structure, Algorithms, Operating System, Probability, Statistic, and Python Programming. So I'm not going to give you a specific course numbering. This is just some generic courses in mathematics and computer science. So what you see on the table is that you have Calculus 1, which abbreviated as CA, Discrete Mathematics abbreviated as DM, so on and so forth. So on the table, wherever you see the X, that means there's some conflict between the two courses. So the X represents the conflict between two courses. So that means that there is a conflict between Calculus 1 and Discrete Mathematics. There's conflict between Calculus 1 and Linear Algebra. There's conflict between Calculus 1 and Data Structure, so on and so forth. And again, what we try to do is that we try to avoid these conflicts, and we want to minimize the time we use to schedule these courses. So now what we do is that we turn this information from a table into a graph. So this is what we want to see here. Again, the abbreviations represent the courses that you see in the table. So let's go over something here. So as we see on the graph, CAs represent Calculus 1. So Calculus 1 has conflict with Discrete Mathematics. Calculus 1 also has a conflict with Data Structure. Calculus 1 has conflict with Linear Algebra, and Calculus 1 has a conflict with Probability, and so on and so forth. Again, what can we do to avoid conflict? Right. So to avoid conflict, what we do is that we apply graph coloring, or more specifically, vertex coloring. And the vertices are adjacent to one another should have a different colors. So we're gonna start from right to left, or it doesn't matter. You can do it from left to right, anywhere you want, as long as you keep in mind that the adjacent vertices should have a different colors. So let me start with Calculus 1. So Calculus 1 has pink, and the vertex adjacent to that has to have a different color. So DM has to have a different color, LA has to have a different color, PR has to have a different color, and DS should have a different colors as well. So DM, let me use blue here. PR should have red. Any colors you like, as long as they are different from one another. And LA should be orange. DS should be purple. Alright, so now we are done with CA because there's no other edges coming out of CA. Now we're going to move on to DM. The adjacent vertices to DM is PY and CA. DM and CA already have different colors. PY should have a different colors compared to DM. But because PY and CA are not adjacent to one another, because no edges connecting the two vertices, what we can do is that we can use the same colors for PY as for CA. We're going to also use pink. Now we're done with DM. We're going to move on to, let's say, ST. So ST should have a different color as LA, should have a different color as OS. Let me use pink here as well because ST is not adjacent to PY or CA. Then I can use blue here for OS because I need a different color. Alright, so now I'm done with ST. I'm going to move on to LA. So LA different from CA, LA is different from ST, LA different from PR, and LA is different from OS. So we're done with LA. I'm going to move on to DS. So DS and PY have different colors. DS and OS have different colors, so on and so forth. So DS, LA, DS, CA. So we're done with DS. And we're going to go to OS. So OS is blue, different from DS, different from PY, different from ST, different from PR, and OS with AL. So you need to find a color, or choose a color for AL so that it's different from pink, different from blue, and different from red. So I can use orange here, or I can use purple for that matter. Okay, so how many colors have you used? So we use, let me see, there's a pink color, there is red, there is blue, there is orange, and there is purple. So we use 5 different colors. And because we use 5 different colors, the chromatic number of the graph So when you do this graph coloring or the vertex coloring, what we see is that I can schedule the same time for CA, for ST, and for PY. I can schedule the same time for the course DM and OS. I can schedule the same time for AL and LA. And because DS and PR have different colors, so they can assign to a different time slot. So certainly this is one version of graph coloring. You can have a different versions of this particular graph with different colors. One of the things that I just noticed is that you can switch out the color of purple and use red for DS because DS and PR, they are not adjacent to one another, so you can use the same colors, right? And when you do that, we reduce the chromatic number down to 4 instead of 5. So let me do this. So a different versions of this graph. So a different version of this graph is that I can eliminate purple and use red. And because we only use 4 colors in this case, I can say that chromatic number is equal to 4, which is a lot better than the first case that we did where we have the chromatic number to be 5. So to recap, what we just did is that we cannot schedule 2 courses at the same time if there is a conflict, and we want to use as few separate times as possible, meaning that in terms of vertex coloring, we want to use as few colors as possible. So as the first try, I have 5 different colors, which is true. It's not wrong. It's just that it's not optimal for the final results. And in this case, we have chromatic number equal to 4, which is a lot better than the first try. Okay, now I'm gonna move on to some other example. It's more generic example just to get ourselves familiar with graph coloring or vertex coloring and the calculations of the chromatic number.